All right, so our next talk is going to be by Sevag Gharibian, and he's going to tell us about dequantizing the quantum singular value transform, some word that I'm not totally sure what it is, and applications to quantum chemistry and the quantum PCB conjecture.
I guess I should get rid of this thing, right? This box, or
if you can, I mean.
I always can. Okay, thanks. Good. Okay, good. So thanks very much for the introduction, Robin. This is joint work with Francois and Gall. My name is Sevag Gharibian. Most people can just call me Sev, first three letters. So let's begin. Okay, what is the theme of this work? The theme of this work is this very natural question, which we've actually heard about quite a bit today, which is, where is the boundary between the power of classical versus quantum computation? Right? It's one of the most natural questions in our field. It's, of course, a really broad question and a very loaded question. So we need to sharpen that question for this talk. So in particular, we're going to focus on three guiding questions. The first one is, well, how do you even rigorously define a notion of such a boundary, right? And there are two examples that we'll touch on this work. One we've heard about all morning, all first session, the first parallel session talked about quantum supremacy, right? And the other kind of way you could do such a formal rigorous definition is via so-called dequantization, and that's something we'll touch on in this work. So that's the first guiding question we'll think about. The second one, of course, is that ideally we would like a practically meaningful such boundary, right? So I think if you ask most people in this room, how would you demonstrate quantum supremacy to somebody who cares, right? You would run Shor's algorithm, right? Because we don't believe classical computers can factor efficiently, right? But the problem is, of course, we're not at a place experimentally where we could run Shor's algorithm on a large scale, right? So you might ask, in the shorter term, is there something practically motivated for which we can try to demonstrate so-called quantum supremacy? Okay, that's question two. And question three is, anytime you have a boundary between classical versus quantum computation, there's an adjoining question that kind of hides underneath it, which is, what does this say about the physical models, right, underlying the two computational models, right? And so, this infamous quantum PCB conjecture, which has resisted efforts for years, right? One way you could interpret this is as saying that natural quantum systems can be exponentially complex even at high temperature. Okay, so these are the three guiding questions for this work, and the point of this work is to tie these together into one thread, okay? And so on this slide, I'm going to, at a high level, very informally just state kind of what are the main points of this work, and then we'll go into more detail. So the first thing is, we're talking about, the boundary between classical and quantum computers, so I need to tell you where the boundary is going to lie, right? So the boundary is going to be this computational problem GLH. It's going to be a practical problem, or at least that's the idea. And we've taken it out of quantum chemistry. So we're not quantum chemists, let's be clear, neither Francois or I. But we talked to the quantum chemists, basically in this where this comes from. And to be clear, this problem GLH, which I have not defined yet, in order to solve it to the precision needed for quantum chemistry applications, you have to solve it to within 1/poly additive precision in the size of the system. Okay, so this is the first thing we'll do. We'll define this problem GLH. Okay, and then we'll show a positive result, which is that if we're willing to be sloppy, meaning I'm not going to solve it to within that 1/poly accuracy, but just constant precision, then classically you can solve this problem. If, okay, there's a big if, you get to add to your computational model these so-called sampling assumptions, which nowadays are kind of more or less becoming standard in our field. And the way we do this is via this so-called dequantization of the quantum singular value transform in the case of sparse matrices and constant precision. Okay, so but that's for the sloppy case that's not constant error. If we go back to the case that quantum chemists care about, we can show that in fact that this is very unlikely to happen now. Okay, where it's going to be worst case BQP hard to solve it to within that 1/poly precision. Okay. And the last thing I'll touch on is, what does all of this say about quantum PCB? Okay, so let's begin. I need to start by defining this problem GLH, right? So for those of you familiar with Hamiltonian complexity, you can probably guess that the LH, or what it stands for, right? I'm not going to give a prize for that. So the K-local Hamiltonian problem, you've probably seen this before. If you haven't, here's the definition, right? In this problem, I give you a local Hamiltonian, H, right, on n qubits, I give you two thresholds, alpha and beta. It's very important that those thresholds are not too close together, right? They have to be at least 1 over poly separated. And your job in this problem is to tell me, is the smallest eigenvalue of H, or in other words, the ground state energy of H, is it small? Is it at most alpha? Or is it big? Is it at least beta? Okay, this is the local Hamiltonian problem. It is the canonical QMA complete problem, meaning the quantum analog of NP. Okay, we've known that for a long time. And let me just mention, I said that this 1 over poly gap is very important. You might ask, what happens if you just demand a constant gap, right? Let's be sloppy in our approximation of the ground state energy. And then you fall into the regime of the so-called quantum PCB conjecture. And it's conjectured that in this regime, the problem should still be QMA hard, but we don't know how to prove it. What is certainly true, kind of straightforwardly, is that once you have the classical PCB theorem, which we do have, this problem is at least NP hard. Okay, so that's the local Hamiltonian problem. This is what us theorists play with in theory, what I like to call theory land, right? In this magical universe where everything functions the way we want. But of course, on Earth, there are actual quantum chemists actually doing real work, right? Unlike us, and they need to solve this local Hamiltonian problem, right? Like, it's actually important in quantum chemistry to solve for these ground state energies, right? They don't care about worst case results. They need to do something, right? And so what do they actually do? So the typical approach, as far as we understand it, is the following. The first thing you do is you use some classical heuristics, okay, to compute a so-called guiding state psi. Okay, think of psi as an approximation to your ground state. Okay, let me be clear. These are heuristics. They run in classical polynomial time, but there's no guarantee that psi is actually a good guiding state. Right? You cross your fingers, hope for the best. In practice, the best is usually good enough. Okay. And so the idea is, once you use heuristics compute psi, well, now you have an approximation to your ground state. You have a quantum computer at your disposal. You want to compute some eigenvalue. What are you going to do? Well, those of you with background in quantum algorithms probably can guess already. You'd run quantum phase estimation, right? That's the obvious thing to do. And so this is kind of the approach we'll take in this work. There's also more recent variational approaches, which I will not touch on. Okay, good. So this is the problem we want to formalize. So let me formalize the problem. Here, it's basically the local Hamiltonian problem, except for what you see in red, right? So in addition to the Hamiltonian H, I also give you your guiding state psi, and I promise you that psi has some delta overlap with the ground space. Okay. Now let me be very clear that I could care less where psi came from. Like some guy could have just walked in off the street and given it to you. I don't care. Okay. And you don't need to verify that this is true. This is a promise. This question is just asking, imagine you had psi at your disposal and you knew that this property held. How hard is it to solve the local Hamiltonian problem? Okay. Okay. One thing I've left out for the computer scientists in the room, you probably are glaring at me with big beady eyes, is what do we mean by representation? Right. That's very important. And we'll have two representations in this work. The first is that if we talk about sampling access, and I'll define these, then this is where we get that classical solvability to within constant precision. And if we have something called a semi-classical state, which again I'll define, then we have that BQP hardness result in that regime chemists care about 1 over poly. Okay, so this is the GLH problem. This is the boundary that we're going to study. Okay, good. So sorry, I had to put a picture of a punching hamburger on this thing. So let me just take a moment to tell you the punchline. Okay, at this point, so we can show that GLH with 1 over poly precision is BQP hard, right? At the same time, it's known that it's in BQP. You can solve it efficiently quantumly. So in other words, GLH with 1 over poly precision perfectly characterizes the power of what it means to do efficient quantum computation, right? And so, we just had a whole session of quantum supremacy. So the obvious question that should be at the top of your mind is, here I have a practical problem, and it captures what it means to be an efficient quantum computer. Can we use this in the short term to demonstrate quantum supremacy, right? And you'll notice I have a question mark at the end of that statement. And not only is it a question mark, but it's a red question mark. And that's because it's a very serious question mark. It really is an honest question, because there's a very serious caveat here, right? Our results are worst case results, hardness results. Okay, so they're like the first baby steps towards quantum supremacy. all the talks you heard earlier, they're typically talking about a much higher bar of hardness you need, right? Like average case hardness with noise assumptions and so forth. Okay. Nevertheless, we can ask this question. I think it's a nice question to ask. Okay, so that's the problem GLH. Let's go into our results regarding GLH. First, let's talk about the hardness of it. And so to talk about the hardness, remember what I have to do is I need to put GLH back on the slides at the top, but I need to specify what type of representation I'm talking about, right? Because I left that gray earlier. So in this representation, we'll talk about semi-classical states, and we totally made that word up. What it basically means is a very simple class of states. If you're familiar with this work of Grillo, Karenitis, and Sikora, it's what they call a subset state, okay? And basically that means that all you do is you take a subset S of strings, right? And you just take an equal superposition over those. And the one kind of difference in our paper versus the Grillo et al. Paper is that here we demand that the subset size is polynomial, and that way the subset state has poly size to describe classically, right? Okay, so that's what we call a semi-classical state, and our claim is that basically this guided local Hamiltonian problem, when I give you as a guiding state, I give you one of these semi-classical states, and I promise you, that the semi-classical state is a very good approximation. It has, even constant overlap with the ground space. Even then, this problem is going to be BQP hard. Okay, that's the claim. So I'm not going to go through the full proof. I'll just very briefly sketch the main tools we use on the next slide. It's not too difficult to show this. So up top is just the theorem I stated. And what's the goal of any kind of hardness proof? The goal is always the same, right? In this case, we want to show BQP hardness, so I've got to take a BQP circuit U, and I have to map it to an instance of this GLH problem, so a Hamiltonian, right? And a guiding state psi. And the properties I need are, twofold, right? Number one, if U accepts X or rejects X, then I need the ground state energy to be small or large, respectively, right? This property is super easy to get because other people have done the work for us. In particular, Kitaev, with his celebrated quantum Cook-Levin theorem, basically his circuit Hamiltonian construction literally gives you this. That's done. You just plug it in. Okay. The additional challenge in our case, of course, is the right side here, which is that we also need to have a guiding state that has good overlap in both the yes and the no cases with that ground space. Okay. And so we need to modify this construction a bit more. It's not too difficult, but what we're going to do is we're going to steal somebody else's work. So Anders Sambinus in 2014 started this really nice line of work on this complexity class p to the QMA log. And one of the tools he introduced there was this so-called block encoding. All I'm going to tell you is why is this useful for us? Well, typically with these circuit Hamiltonian constructions, in the yes case, I have a good idea of what the low energy space looks like, but in the no case, I don't. And so then it's kind of hard to design the guiding states. But with this block encoding trick, you can pretty much design the ground space in the no case as well to look exactly like what you want, and then designing the guiding state is easy. Okay, but that's all I have time to say. So this is just to reiterate, we can show that this problem is BQP hard if you want that 1/poly precision. Okay. The flip side is the classical tractability when you have constant precision. So again, I need to restate the problem, and I need to tell you what is the representation of the state we're talking about. It's going to be a so-called sampleable state. And note that our algorithm will work not just for local Hamiltonians, but also more generally for sparse Hamiltonians. So what is a sampleable state? Okay, so this is a big and ugly definition. I literally just copied it out of the paper. But the point is, for the purposes of this talk, you can set this zeta over here as an error parameter, okay? So here we're like showing off by saying, oh, look, our algorithm works even with some error zeta, right? But for this talk, just imagine that zeta is 0. Just imagine it's perfect, okay? And then you can ignore this third condition as well. And I'll focus on just these two, okay? So perfect sampling, what does it mean to have perfect sampling? Access to some state psi. So two things. The first one you're probably familiar with, query access, right? You give me an index I in this vector, and I give you the ith amplitude in that vector psi I. Okay, that's pretty standard. Of course, this alone in some sense is pretty useless for a classical algorithm because the number of indices is huge. I'm poly time. Where am I going to look, right? So that's where the second assumption comes in, right? Wouldn't it be nice if somehow, some magic way, I had to figure out what are the important entries in that vector, so I can focus my attention there, right? And so that's what sampling access does. It basically says that we can sample efficiently from some distribution classically that essentially points out what are the heaviest elements in this vector. Okay, so the probability of seeing an index j is basically the amplitude squared of psi j. Okay, that's sampling access. So these two alone are what we're going to use. When zeta equals 0, the case that we're talking about right now, this is basically Tang's original definition. Okay, so our guiding state is going to be of this form. And what we claim is that in the constant precision setting, we can solve GLH efficiently classically with the assumption that we have a guiding state that is sampleable. And this is basically a sketch of the main parts of the proof and how they fit together. Okay, obviously I can't go through the whole thing, but the main thing first is we reduce GLH to something more general, right? We reduce it to estimating singular values in the guided setting, right? And I hope you believe me that GLH is just an eigenvalue problem, so obviously that should reduce to singular value estimation, which is more general, right? Again, constant precision, of course. And then we reduce this to the so-called dequantization of the quantum singular value transform. This is what I'll talk about on the next slide. To go from here to here, there's one step that I won't have time to talk about. You need to process your Hamiltonian with a constant degree polynomial. And what this essentially does is it kind of tears apart the singular values in a nice way so that you can distinguish the two cases you need to distinguish. And the key point is that the polynomial we choose can be constant degree precisely because we're in the constant precision setting. Okay, so let's talk about this last one here. Okay. So another big ugly definition, I'll point you to what's important. This is what we'll call the singular value transform. There's absolutely nothing quantum about it. Okay, it's just a classical definition. Intuitively, all this is saying is the following. So imagine I have sampling access to two states for simplicity, U and V, two vectors. And I have query access to this sparse matrix A. That's this bad boy over here, right? And your job is to estimate this overlap, V dagger P basically times U. That's the name of this game. P is some polynomial, right, of some degree D. Okay, and so if you're wondering what the connection to the quantum singular value transform is, that's just basically a quantum algorithm that produces the state P times U. That's what the connection is, right? But in principle, this statement has nothing to do necessarily with the quantum analog, right? And so what we show is that this value can be estimated to within constant precision, well, more generally within that time to within whatever precision epsilon you want. And note that, of course, if the degree D is constant, then this will be a poly runtime as long as the sparsity is polynomial, of course. Okay, good. So I'm just going to sketch this proof very quickly. It's how do you estimate this quantity over here? It's quite natural. This is just an inner product, right? It's the inner product of V and P times U, right? What's an inner product? Well, it's just the sum of a bunch of terms, right? You multiply two things, you add it, and then the next index you multiply and you add, and so forth, right? The only problem is this thing has an exponential number of terms in the sum. But if you've got access to randomness, so the obvious thing to try is, pick random indices, like pick a random term on the left, a random one on the right, multiply, add, and rescale, and do this just for a small number of random entries in that giant sum, and hope that your rescaled mess is approximately correct. And this is exactly what we do. This is kind of a standard thing to do. Repeat the following R times. So on the left-hand side, I'm going to pick a random entry of V. Okay, and here it's very important. I have sampling access, which guides me directly to the heaviest elements of V, the most important elements of V. Okay, so I don't waste time. I'm not messing around, right? So I get a good index J, and then via the query access, I can compute the actual entry at Vj now. And then, of course, I need to compute the corresponding entry on the right-hand side over here, the jth element there. And that one takes a bit of work. I'm not going to show you how that's done here, but you can do it using a recursive technique. And it's very important that this matrix A is S-sparse, right? So we compute the jth entry of that nasty thing over there, classically. And finally, we just do some rescaling and add it to our running total. Wave the magic wand, apply Chebyshev's inequality, and you can show that this thing will be within the desired error bounds with high probability, yada, yada, yada. Okay? So this is how we prove, this is just part of that proof, just the very last part of how you dequantize the quantum singular value transform in order to estimate the guided local Hamiltonian problem to within constant error. Okay, so I'm just going to take I don't have any open questions at the end, so I'm just going to take that time instead to just very briefly tell you about the connection to the quantum PCP conjecture. So remember, the quantum PCP conjecture is just in this setting. It's the local Hamiltonian problem, but you ask, what happens if we're very sloppy? We just want constant error in estimating that ground space, ground state energy. It's supposed to be QMA hard, but what we show is that exactly in this regime, right, constant error, if you have access to one of these good guiding states, these sampleable guiding states, then there's no way this quantum PCP is going to hold, because the local Hamiltonian problem, actually falls into a smaller complexity class MA. Okay? And so obviously there's a big if here, if there's a good guiding state, right? Nobody expects this thing to exist. So when you don't expect something to exist, but you can't prove it, what do? Well, you come up with a conjecture, right? Sorry, I don't know if you guys can see the title. Okay, anyway, so we're going to blatantly copy the NLTS conjecture of Friedman and Hastings. So if you're not familiar with this conjecture, it's very natural. It basically says, look, if you believe the quantum PCP theorem, at a very bare minimum, what has to hold is the following, right? It has to be true that there has to be at least some family of local Hamiltonians whose low energy states basically don't have a classical description, a good classical description. And in particular, they can't have constant depth circuits. And we're literally going to copy this. In fact, we're even going to copy like the structure of the acronym. It's NLSS instead of NLTS. And it's the same statement, literally. The only difference is instead of having your low energy state be preparable with a constant depth quantum circuit, what the theorem on the previous slide suggests is that there should not be a good guiding state with good sampling access, because otherwise you could solve for the ground state energy of H in MA. Okay, and so what I find kind of neat about this is just that these sampling assumptions have been used to break a lot of quantum stuff in a very successful way, right? And like quantum machine learning and so forth, you could dequantize a lot of it. And quantum PCP has been a stubborn nut to crack. So wouldn't it be interesting if kind of the straw that broke the camel's back was the exact same assumption that broke things like QML and so forth, right? This sampling access, right? But we have no idea how to prove this, and to be honest, we haven't thought seriously about it yet. That's it. Thank you for your attention.
All right, since we started a little late, maybe we can take a question or two.
Don't worry, it's up to you.
Hi, thanks for the talk. I was just gonna ask about, so this size of the polynomial in the, you require this 1/poly gap.
Yeah.
So my understanding is a lot of times in chemistry, they want the precision to be on the order of like the energy of a single term in the Hamiltonian.
Yeah.
But I feel like the polynomial that you have in your proof, would that be a smaller precision?
I mean, normally we're imagining here that you rescale the Hamiltonian so that it has constant norm, and then that gets converted to a 1/poly gap. You're completely right? I mean, but to make things well defined, like what does it mean to say 1/poly? You have to first fix the norm of the Hamiltonian somehow, let's say to 1. So we've done that pre-transformation in our minds.
Yeah, so I guess that my question is, if you wanted to like make that polynomial big, or the inverse polynomial big enough that the precision needed for the hardness result is like, constant, like 1 over the number of terms, would that be like doable, do you think? Or because this might be what the chemists want to achieve with their experiments. And
well, I think it is already scales like that, if I'm not mistaken. I have to double check, but
okay.
I think it kind of does. I mean, like these hardness, Kitaev's construction, like the gap scales with the circuit size typically, and that's proportional to the number of local Hamiltonian terms.
Okay,
yeah.
Great, thank you.
Linking back to your quantum chemistry motivation at the beginning.
Okay.
Would you have this perfect sampling access for these Hartree-Fock type of states? So would those be candidates for this?
I don't know for sure. I'm guessing the answer is yes. I mean, typically, like for the subset, for the semi-class